Hi, welcome to another PYQ discussion video. And in this video, we are going to discuss 2 marks and 3 marks of the chapter Nuclei from 12th physics. Okay, see, let's move on to the first question. Define the term distance of closest approach. How will it be affected for an alpha particle? The particle is doubled. So we have 2 parts for the question. First one is to define what is the distance of closest approach. We know the distance of closest approach of a given alpha particle. In alpha particle scattering experiment, we had the gold nucleus, right? So this is the nucleus of the gold foil, and an alpha particle approaches this nucleus with a kinetic energy Ke, right? Alpha particle has a kinetic energy, it is moving towards the gold foil, and we know when it approaches in this way, its impact parameter is equal to 0. Impact parameter is the distance, the perpendicular distance between the directions of alpha particle and the line passing through the center of the nucleus. We know that if impact parameter is 0, the alpha particle is actually heading to a collision, a head-on collision with the nucleus. That is what expected. And those alpha particles are expected to bounce back, right? In the experiment, we observed very few alpha particles bounces back with theta 180 as the scattering angle. And for that, impact parameter should be what? 0, right? Okay. Then, see, such a alpha particle approaches the nucleus. And we know when it approaches the nucleus, alpha particle also has positive charge, right? See, charge of alpha particle Q1 is going to be plus 2e, right? Because alpha particle is consisting of 2 protons and 2 neutrons. 2 protons have charge E each. So 2e is the total charge. Q2, charge of the gold foil is going to be Z. Z is the atomic number times the charge of 1 proton, right? Because there are Z number of protons. So Ze is the charge of the second. And now when this alpha particle approaches the nucleus, we know because of the repulsive force, it loses its kinetic energy. That means it slows down. And finally, it comes to rest at a particular point. Here, the body comes to rest. Speed is keep on decreasing, right? Because of the repulsive force, we know. And it cannot go further towards the nucleus. So this distance was considered to be the distance of closest approach, where kinetic energy of the alpha particle becomes 0. And that kinetic energy will be completely converted to electrostatic potential energy between the nucleus and the alpha particle. So we know we defined distance of closest approach as kinetic energy of alpha particle is equated to, we derived that equation by equating kinetic energy of alpha particle with potential energy of alpha particle and nucleus system, right? So this was the concept behind. Right? So how will you define it? We can define distance of closest approach is the distance between the nucleus and alpha particle. What kind of nucleus? A nucleus with impact parameter 0. Right? The distance between nucleus and alpha particle with impact parameter 0, where its kinetic energy reduces to 0 and it is completely converting into the potential energy. The alpha particle cannot go beyond that particular point. So that is the closest point that alpha particle can go. That is how we define distance of closest approach. How did we obtain the expression for distance of closest approach? That is from this kinetic energy of alpha particle. Let me take it as kinetic energy of alpha particle as this is equal to potential energy of alpha nucleus system. Alpha particle and nucleus system means we know electrostatic potential energy is K times Q1, Q2 divided by R. That is the equation. So here K is the constant 1 by 4 pi epsilon 0, right? Electrostatic constant into Q1 is 2E. And what is Q2? It is Z times E divided by D. Okay, so we got 2kz E square divided by D, where D is the distance of closest approach, right? At that D only we can equate kinetic energy of alpha and potential energy of alpha particle and nucleus system. That is how we got this equation, from which we can find out distance of closest approach D as 2 times kz E square divided by kinetic energy of alpha particle, right? So this was the answer for the first part, the distance of closest approach we defined. Now, the second part of the question is about for an alpha particle, how will it be affected? That means how will the distance of closest approach be affected for an alpha particle if the kinetic energy of the particle is doubled? Okay, look at this. Alpha particle's kinetic energy is coming in our calculation in the denominator, right? Kinetic energy of alpha particle. What happens if the kinetic energy is doubled? The d dash will be equal to 2kZe square. None of these terms will be changed because like k is the electrostatic constant, we know 1/4πε0. Z is the atomic number of the gold, 79. E is the charge of alpha, like proton. They're all constant. What is the only difference? 2 times kinetic energy of alpha particle, right? Kinetic energy of alpha particle is doubled. So what is d dash? D dash is going to be just half of the initial distance. Correct? So the new distance of closest approach will be half of its initial value when the kinetic energy of the alpha particle is doubled. Right. Okay. So moving on to the next one. A proton of energy 1.6 MeV approaches a gold nucleus. Z is equal to 79. Find the distance of closest approach. Okay, you are given the kinetic energy of the particle approaching. You are given atomic number of the target nucleus. See, we know both the values. And just now we derived expression for distance of closest approach. D is equal to 2 times kZe square divided by kinetic energy of that particular particle. Here it is a proton. So we can take kinetic energy of the proton as it is. 1.6 MeV. Right. Okay. See, when we substitute these values, we are looking for the distance, right? A closest approach, distance of closest approach. And the values we are going to substitute in this one, K is 9 into 10 raised to 9, we know. And that is like for the SI units. Z is 79. Charge of electron is in Coulomb, right? So all SI values we are going to substitute. Therefore, given kinetic energy, which is in electron volt, should be converted to SI units, which is joules. So we can say kinetic energy is 1.6 MeV is the given unit. So 1.6 MeV, first of all, I will convert that into electron volt. This is mega electron volt. Now we can write it like 10 raised to 6 electron volt. Now that electron volt value should be converted to joules because we are looking for the value in SI unit. 1.6 into 10 raised to 6, that is the value in electron volt, into converting electron volt into joules, multiplying with 1.6 into 10 raised to minus 19, correct? Now the value will be converted into joules. So we have kinetic energy value as 1.6 the whole square into 10 raised to minus 13 joules, right? 10 raised to minus 13 joules. So this is the kinetic energy value in joules. I told you why should we convert that electron volt into joules, because all other values we are going to substitute in SI units. Now what is D? D is equal to 2 into K. We know the value of K, electrostatic constant, 9 into 10 raised to 9, into Z is given 79, right? 79 into E square. E is the charge of electron, 1.6 the whole square into 10 raised to minus 19 the whole square, right? The whole divided by, what's the kinetic energy now? 1.6 the whole square into 10 raised to minus 13, correct? That is the given values. Now 1.6 whole square gets cancelled. We have 2 into 9 into 79 into, look at the powers, we have 13 plus 9, we get 10 raised to 22, right? Into 10 raised to minus 38, because we squared 10 raised to minus 19, right? Because E square was the value. So we have 218 into 79 into 10 raised to minus 16, meters. Okay, so that will be your distance of closest approach. We simply substituted the values. All values were given in the question. With one small point, I wanted to remind you, conversion of electron volt value into joules, because all other values we substituted in joules only. Okay, all right. Then draw a diagram to show the variation of binding energy per nucleon with the mass number for different nuclei and mention its two features. Why do lighter nuclei usually undergo nuclear fusion? Again, two parts we have for this question also. The first part of the question is to draw the graph. The graph which represents variation of binding energy per nucleon with the mass number of the nucleus. See, binding energy per nucleon is taken along y-axis and mass number is taken along x-axis, right? That is how we draw the graph, and we know this is like 2, 4, 6, 8, 10, 12 and so on. Remember, the unit is in mega electron volt, MeV, and here we marked this as 50, 100, 150, 200, 250 and so on, right? The mass number. This is how we represented the range of mass number along x-axis and the value of binding energy per nucleon along y-axis. And we know to take 8. See, this is the reference line we have to remember, 8 MeV. Because in the observation, we concluded by looking into this graph that almost all the nuclei has an average binding energy of 8 MeV. So 8 MeV is the reference line for our binding energy per nucleon graph. Okay, and now we will mark 2 points in the graph. One is the point which is somewhere close to here, 30, mass number 30, okay? And another point we have to mention is mass number 170. Okay, these are the 2 points we have to remember in the graph. One is 30 and one is 170. Those 2 reference points you have to keep in the graph. And when we start from here, the graph should cross the 8 MeV line around at 30, like, mass number value 30, and it goes up to a maximum value near somewhere here. And then it goes almost a constant, and it again comes below that 8 MeV line after 170. Okay, that is why we marked 2 reference points here, right? 30 and 170. Right. See, we have some like graph, like, peak occurs in this region, and even if you don't represent that in the graph, usually you get marks. Okay. Right. It is because of some special magic numbers there. Some specially like stable nuclei are coming in this range. Okay, so, and the highest value, highest value in the graph is somewhere here, and that value is found to be 8.8 MeV, correct? 8.8 MeV. So this value also you have to mark in the graph, okay? And that is given as Fe56. This is for Fe56. Highest point in the graph is for Fe. So most possible binding energy per nucleon is for iron 56, and its value is 8.8 MeV. Even if you don't represent those elements here in the nuclei here, that's okay, but this you have to represent. Okay, the highest binding energy per nucleon is for iron 56. Okay, so this is about the graph, binding energy versus mass number graph. Okay, and as I told you, most of the elements has an average binding energy of 8 MeV, right? And if mass number is less than 30 or greater than 170, binding energy per nucleon comes down below 8 MeV line. Okay, so the first part of the question was to draw this graph. Good. Now, why do lighter nuclei usually undergo nuclear fission? That is the next part of the question, B. So simply in one single statement, we can say the answer to attain stability, right? Or to be more stable. And how it is explained using the graph. We know the lighter nuclei, whenever they get a chance to combine together and to go to the next level, to the next element, they will get more binding energy. Correct? Whenever they combine, whenever they undergo nuclear fusion, it becomes more heavier element. Heavier element will have more binding energy. Correct? It will have more binding energy per nucleon, which means it will have more stability. That's the reason. Correct? So the lighter nuclei are ready to fuse together so that they gain more binding energy per nucleon, and hence they'll be more stable. Okay, so we answered both part of the question. First one was the graph. Second one is about why do they so. Good. Next one. Prove that the nuclear density is same for all nuclei. See, the same question we had in the MCQ discussion part. In that video, I already did that. But still, we'll go for that proof. Like, what is the, how will you prove density is same for all nuclei? Same for all nuclei means, see, it is independent of mass number, correct? Independent of mass number. That is what you have to show. Even if the mass number changes, even if the nuclei changes, density remains the same. And we know how to calculate density of anything. Density of nucleus is going to be mass of the nucleus divided by its volume. Mass by volume is the density of something. So how will you calculate mass of the nucleus? We know in any given nucleus, there will be A. A is the number of nucleons inside the nucleus, right? Number of nucleons means the total number of protons and neutrons inside the nucleus, right? That into atomic mass unit. What do you mean by atomic mass unit? It is the average mass of one nucleon, correct? Yes. So average mass of one nucleon into total number of nucleons will give you total mass of the nucleus. So the numerator is A into U. Look at the denominator. It is volume. Volume is 4 by 3 pi r cube. We consider nucleus as a spherical shaped core of the nucleus of the atom, right? So radius of that particular sphere is r, then volume will be 4 by 3 pi r cube. And we have one substitution here. Radius r is equal to r0 a raised to 1 by 3. Radius of the nucleus, correct? In terms of mass number. So if you substitute that there, A into U divided by 4 by 3 pi into R0 A raised to 1 by 3 the whole cube. Good. See, in this case, see, we will get 3AU. I'll take A to the numerator. 4 pi into what comes next? R0 the whole cube, right? R0 cube into A. A raised to 1 by 3 the whole cube. A raised to 1 by 3 the whole cube becomes just A only. So now A gets cancelled. Look at this density equation. We get 3 into atomic mass unit divided by 4 pi into R0 cube. See, look at this. 3 into 1 atomic mass unit is going to be 1.67 into 10 raised to minus 27 kilogram divided by 4 is the numerical constant. 3.14 is the phi. And now what is R0? R0 is going to be 1.2 into 10 raised to minus 15, correct? The whole cube. Look at this. Is there any variable? No. See, all of them are constants only. So if all terms are constants, we can say nuclear density is independent of mass number. Even if you change the nucleus, that doesn't affect this calculation. It is independent of the mass number. For all nuclei, density remains the same. This is how we prove that. Okay, so that was the first part of the question. Now the second part of the question is draw a plot of potential energy of a pair of nucleons as a function of their separation. Draw two inferences from this plot. Again, the question is about a graph. The previous question also about, we had another graph in that question. It was binding energy versus mass number graph. One of the repeating question from this chapter. This is another repeating graph from the chapter, which we are going to do next. That is the potential energy versus internucleon distance graph. Okay, so we draw the graph by taking potential energy along y-axis and internucleon distance along x-axis. Remember, this internucleon distance is taken along y-axis in femtometer or Fermi, 10 raised to minus 15 meters, right? That is a range, right? And potential energy is taken along y-axis. This is positive potential energy. Along negative y-axis, negative potential energy. Here potential energy will be 0. Okay, so now the R value we have given, see, this is 1 FM, 2 FM, see, values will be 1, 2, 3, 4 and so on, right? In FM, in femtometer or Fermi. Okay, now what exactly is the graph all about? See, we have two nucleons. Two nucleons could be either proton-proton pair, neutron-neutron pair, or even proton-neutron pair. Doesn't matter. See, we know that force remains the same. It is independent of the particles or independent of the charge. Right. So this is the distance between the two, r. What happens to the potential energy of these two particles when we move them, like, with respect to each other? When I increase the r value from 0, if I increase it from 0 to some maximum value, then how potential energy of the system be affected? That is what we have represented in this graph. And we know, see, the potential energy decreases to 0 and then increases in the opposite direction. So the points you have to remember, mark one point close to 1 FM, which is actually 0.8 FM. So it should be close to 1 FM, right? 1 FM. So it's 0.8 FM. That is a one reference point. And the next reference point you have to remember is 3 FM. Graph should end at 3 FM. So it decreases like this and crosses, and this is how the graph can be represented. See, crossing the x-axis at 0.8 FM, and the graph approximately, like, it almost ends at 3 FM. So beyond 3 FM, graph should not come. Okay, so then this graph represents variation of potential energy versus internucleon distance of a given pair of nucleons. That is the graph. Okay, now look at the second part of that B question. Like, draw two inferences from this plot. See, by looking into this plot, we have to infer something about the properties of nuclear force or the nucleons, like, some 1 or 2 points you have to conclude from this. So we understood many things from this particular graph, So one of the points we can mention is potential energy is negative, right? For what range? See, the range of distance between the nucleons, if it is between 0 and 0.8 FM. See, this range. I'm talking about this part from r is equal to 0 to r is equal to 0.8 FM. In that range, what about the potential energy? Potential energy is found to be positive. Correct? Potential energy is positive. And remember, whenever potential energy is positive, nuclear force is repulsive. Right? If potential energy of two masses or two particles is positive, that means the force interacting between them is repulsive in nature. That is why if potential energy is positive, it is repulsive. Right. Another observation we can make is when r is equal to 0.8, r is equal to 0.8 FM, what about the potential energy? It is 0. Potential energy is equal to 0 means it is a stable position, If potential energy of the system is 0, it is in the stable condition. So that is the most stable distance between the two nucleons. Correct? 0.8 FM is the most stable distance between two nucleons. Now what happens if the distance increases from 0.8 FM less than r and less than 3 FM? Look at that part of the graph. If it is less than 3 FM, we have up to this 0.8 to less than 3 FM. In this range, potential energy is actually negative. See, if the potential energy is negative, what is the nature of the nuclear force? Nuclear force is attractive, right? That is another conclusion you can make. Right. Now, what happens if R is more than 3 FM? R is more than 3 FM. If R is more than 3 FM, look at the graph once again. See, there is no potential energy after that. So the nuclear force is operating only up to 3 FM. If the distance you increase beyond 3 FM, what happens? Nuclear force disappears. Because we know nuclear force is a short range force, very short range force. In the sense that force is operating only between 0 to 3 FM, right? That is the range of the force. So we infer so many things from the graph, right? Write 1 or 2 points. You're asked to write or infer 2 points from this. You can write any of them. Okay, and one of the repeating graph I told you already. Next question. State any 2 properties of a nucleus. Right. See, that's a very basic question we can answer. We have so many points to write. See, inside the nucleus, we can see protons and neutrons, right? Yes, that is one property. Radius of a nucleus, R, is measured to be R0 a raised to 1 by 3. Density of a nucleus is independent of mass number. That is what we did in the previous question, right? What density? Density is independent of mass number. Mass of nucleus can be measured in atomic mass unit. So many properties we can write. It is a central core of the nucleus. It has a positive charge. So many properties. List any two of them. Right. Now, B part of the question. Why is the density of a nucleus much more than that of an atom? See, density of a nucleus, we solved it in one of the previous questions. Density of the nucleus is in the range of 10 raised to 16 kilogram per meter cube. Okay, it's a very high density region, and it is much greater than that of an atom. Why? Because the majority of the space, what was the conclusion from Rutherford alpha particle scattering experiment? He concluded that majority of the space in an atom is empty, right? Most of the mass, right? Not entire mass, most of the mass. That means except electronic mass, like protons and neutrons are accumulated at the center. So most of the mass is accumulated, concentrated at the center of the atom, which is called nucleus. So most of the space in an atom is empty. So it has, what will be the result? It has wide, it's big volume. Density is calculated as mass by volume, right? So comparing to the nucleus, nucleus has all the protons and neutrons together. So it is the heaviest part of the nucleus. Heaviest part of the atom, and atom is widely spread. Most of the space is empty. So if you go for density of the whole atom, it will be much less than that of density of the nucleus. We have so much space, empty space inside the atom. Okay. Now, show that the density of the nuclear is same for all nuclei. We solved the same question just before. So just show that it is independent of the mass number. Okay. Right. Write two characteristics, properties of nuclear forces. Yes. Nuclear forces, their properties. We have so many points to write. You are asked to write any two. Correct? One is nuclear force is the strongest force in the nature, right? Strongest force, right? And right now, just before in the question we explained, like it is a very short range force, right? It is operating only between 0 to 3 FM. Okay, and then we can mention it is charge independent. That also we mentioned before. Charge independent means if you have proton and proton pair, neutron pair, or proton neutron pair, whatever may be the combination, they have the same nuclear force acting between them. It has saturation property, right? It becomes attractive. Most of the time the force is attractive, and it becomes repulsive if R is less than 0.8. See, we explained in the previous question also, right? Any of those 2 points in the answer. Okay. Now, B part. Draw a plot of potential energy of pair of nucleons as a function of their separation. Write 2 important conclusions you can make from that. See, that is what exactly we did in the previous question, right? Okay, from the graph, we inferred something. Now, the carbon isotope, yes, C612 has a nuclear mass of 12 atomic mass unit. Good. Calculate the binding energy of its nucleus. Yes. How will you calculate binding energy of a nucleus? See, in the MCQ discussion video, we have explained how to calculate binding energy in detail, right? Now, this is the first time we get a binding energy question in 2-mark and 3-mark session. So, binding energy of any nucleus. Be very careful whether it is binding energy only or binding energy per nucleon. That matters because we know it can be calculated differently. At the end, we have divided by mass number. So here it is only binding energy. So binding energy of nucleus is going to be change in mass or the missing mass into C square. Or we know we will multiply that with energy equivalent of 1 atomic mass unit. So delta M into 931 MeV. That is what we have to do. So 931 MeV is ready. We have to just multiply with that. But before that, we should know what is delta M. How will you find delta M? Delta M is the expected mass of the nucleus or total mass of the component constituent particles minus the actual mass of the nucleus. See, actual mass of the nucleus is given for carbon-12 isotope. It is 12 atomic mass unit, right? Then, how will you find out the mass of the constituent particles? We know number of protons into mass of proton plus number of neutrons, which is A minus Z into mass of neutron. That is the total mass of the constituent particles of the nucleus minus the actual mass of the nucleus into 931 MeV. This is your binding energy. So we have to find out what exactly is this value, right? Yes, then we will find out what is, we can finally multiply with 931. So I'll calculate this part separately. So we have delta M is equal to Z into mass of proton. What is Z? See, atomic number is 6, mass number is 12. So proton number is 6, even neutron number is also 6 because 12 minus 6 is going to be 6 only. A minus Z is 6 only. Right, so we have 6 into mass of proton is given 1.007825, right, plus A minus Z is also the same, right, 6 into mass of neutron 1.008665, correct. So this is the total mass of the constituent particles minus what? The actual mass of the nucleus. Actual mass of the nucleus is given as 12 atomic mass unit, right? Yes, just 12.000, just 12 only. Okay, so we have 6 is common. We can just add 1.007825 plus 1.008665. Then you will get something, multiply that with 6, then you will get 12 point something minus 12, that is going to be your delta M. See, we'll come back to this calculation. After finding delta M, you can just multiply with 931, right? So we get 2.1649 here. So 6 into 2.1649 minus 12, right? 12.0. And if you simplify this, you will get 0.09894. This will be 12 point something and this will be 12. So 0.0984 atomic mass unit is the delta M. Now, if you know delta M, now you can find simply what is the binding energy of the nucleus. Binding energy is going to be that delta M into 931 MeV. Okay, so just multiply this 931 is 0.0984, that could be multiplied with 931 and that value will be is in mega electron volt, and if you simplify this you will get 92.11 MeV. Okay, so the rest calculation is easy. So the only thing you should properly write the number of protons and neutrons, then simplify. Okay, this is how we found binding energy of a nucleus. And if the question was binding energy per nucleon, not in this question, if it was binding energy per nucleon, the total binding energy should be divided by the mass number, where mass number is 12 here. Okay, but the question is about only binding energy. Be careful. Okay, next one. Calculate the energy released or absorbed in the following nuclear reaction. See, we know in nuclear reactions, there will be Q value, energy released or energy absorbed. We always calculate that energy as delta M into, see, energy released, which is denoted by Q value of the reaction, right? Q value of the reaction is actually delta M into 931 MeV here also, right? Where 931 MeV is energy equivalent of 1 atomic mass unit. Then delta M in this case, it is not the missing mass, right? It is the difference between total mass of the reactants minus total mass of the products, right? That is how we take total mass of the reactants we'll take, and we'll subtract total mass of the products from that. That will be the delta M, right? Yes, mass of reactants minus mass of products, that is the delta M, into energy equivalent of 1 atomic mass unit, which is 931 MeV. So this is how we calculate energy released in all the processes, right, on nuclear reactions. And if we get Q as a positive value, positive result, that means energy is released. And if you get Q value as negative, that means energy is absorbed. Look at the question, you're asked to check whether it is released or absorbed also, right? Both, there are possibilities, like, it can be either absorbed or released. How will you identify? If Q value is positive, it is a released energy. If Q is negative, it's an absorbed energy, okay? Now let us check in this case. In this question, you are given mass of carbon 12. See, this is actually 2 times mass of carbon 12, right? Yes, it is 12. So we can say delta M. We will calculate delta M first of all, like in the previous question. Then we will multiply with 931 later. So delta M is going to be mass of 2 times mass of carbon 612, because it is no reactants is this only, total mass of the reactants. Now, mass of the products is going to be minus, see, from this we have to subtract the mass of the products. It is like mass of neon and mass of helium, right? This is to be added and subtracted from the total mass of the reactants. So now we have the value 2 times 12 atomic mass unit, right? That is what mass of the reactants, because mass of carbon is given as 12 only, minus what are the other 2 values? It's like mass of neon and mass of helium. See what that values are given, 19.992439 plus that is added to mass of helium 4.002603. Okay, this is the value. So this is 24, right? 2 into 12 is going to be 24. 24 minus this value, if you add them up, you will get 23.995042. Okay, so there is a small difference between the two, right? And delta M is going to be positive only because 24 is bigger than the other side. So delta M is equal to 0.00498. That much atomic mass unit. Yeah, I think 495. It's 0.00498 atomic mass unit. And the rest of the calculation is easy. We know we did the same thing for binding energy calculation also. Now we have the Q value, energy released. Q is equal to delta M into 931, delta M into 931 MeV, mega electron volt. So what is your Q value? That is 0.004958 into 931 MeV, right? That value you have to simplify and we will get 4.62 mega electron volt. That is the energy released in the process. Okay, so this is what you have to do in all the reactions. Take total mass of the products, reactants minus that of the products. That will be delta M multiplied with 931 MeV. Okay, then define atomic mass unit. That is the first part of this question. We know what is atomic mass unit. One atomic mass unit is equal to, see, one atomic mass unit is U or AMU. We represent both the ways. 1 U is equal to mass of carbon 12 isotope, right? Mass of carbon 12 isotope divided by 12. So 1 by 12 of total mass of carbon 12 isotope. Actually, what is this? Mass of carbon 12 isotope in the sense, carbon 12 has 12 nucleons in it. That 12 stands for the mass number, right? Yes. So actually it is mass of how many nucleons? 12 nucleons, right? Because atomic mass is 12 means there are 12 nucleons divided by 12. What do you mean by that? Mass of 12 nucleons by 12 is going to be mass of what? 1 nucleon. So 1 atomic mass unit is nothing but average mass of 1 nucleon, right? Yes, average mass of 1 nucleon. Why did I write average mass of 1 nucleon? If it is 12 nucleons by 12, it should be exactly mass of 1 nucleon, right? But we know nucleons could be either protons and or neutrons. Protons and neutrons are slightly different masses, like what we have seen in the previous questions. So that is why we have taken average mass of one nucleon. That is what one atomic mass unit. And calculate the energy required to separate deuteron into its constituent parts. Here again, you are asked to find out what is the energy required to separate a deuteron into its constituent parts, and constituent parts are protons and neutrons, right? So we have a deuteron given, mass of deuteron given. See, if you have a deuteron, it is 1H2, right? It splits into constituent particles. A deuteron is simply one proton and one neutron, right? That's called a deuteron. Yes, so it will be splitted into one proton, 1H1, correct? That is one proton. And what about neutron? One mass, zero charge, right? So this is how the division or the split of deuteron happens. It splits into one proton and one neutron. Now it is easy. We have to find what is the mass of this deuteron. It is given in the question, right? And we have to go for mass of proton and mass of neutron, sum of the two. Then you will get total mass of the products. Take the difference, multiply with 931 MeV. That is our final answer. Okay, so energy Q value released is equal to delta M into 931 MeV. So we'll go for mass of this, right? Delta M we are going to calculate as mass of that deuteron minus mass of proton, right? This is proton plus mass of neutron. See? So that is the delta M. So we have deuteron mass is given 2.014102 atomic mass unit minus, see, sum of the two, 1.007825 plus 1.008665. So these values we have taken right in the previous questions also. So 2.014102, that is like the first part, and when we add these two together, we get 2.01649. Okay, when we add them up, and we have 2.014, and in this part we will get the difference between the two. If you go for delta M, we have 0.00238 atomic mass unit. Okay, that is the value of delta M. Now, if you want to find out the energy required, see, let me continue here. Energy required Q is equal to delta M into 931 in mega electron volt. So just multiply 0.00238 into 931 MeV, and that is going to be approximately 2.22 mega electron volt. That is the energy required to split one deuteron into one proton and one neutron. Okay, same concept, delta M into 931, correct? Delta M is the difference between masses of products and reactants. Okay, fine. Yes, calculate the energy released or absorbed in mega electron volt in the nuclear reaction. Again, we have given a nuclear reaction here. So same thing you have to repeat. This is total mass of the reactants, and there will be total mass of the products. We'll take the sum of the two, right? And we'll take the difference, that is delta M, and then we multiply that with 931. So energy released or absorbed, like before, it is delta M into 931 mega electron volt. That is the equation. Yes. So first of all, we will calculate delta M. For delta M, we have mass of this one, proton and one tritium here. So we are just going to add them up. So these are the two masses. Be careful when you take the masses. Don't be mistakenly take the other one. See this and this, right? First and third values that is coming in the like left hand side. So we have to go for mass of like H11 plus mass of H13. Yes. Minus on the other side it is deuterium, right? So 2 times into mass of 1H2, because it is 1H2 plus 1H2, right? Okay, so now we substitute the values. 1H1, it is a proton only, 0.07825 plus what is the tritium one? 3 point, that value is given 3.016049. Then sum of these two minus, right, 2 into mass of tritium. So we have 2 into 2.014102. Okay, so we can just add these two and then we subtract, the other term from that. And when you add the first term, we get like 4.023874 minus we get 4.028204. Yes, so look at this. This term is bigger than the other, and definitely we get a minus sign, right? Yes, so the second term is bigger than the first term. So when you subtract this, we'll get minus 0.00433 atomic mass unit. That is your delta M. Okay, just add these two and subtract. Calculation is easy. Now you can multiply that value with, see, Q is equal to delta M into 931. So what is your delta M? Minus 0.00433 into 931. That value will be in mega electron volt as usual. So we get minus 4.03 MeV. Okay, so as you can see, we get repeating questions from this part, like to find out energy absorbed or energy released during a reaction, and also binding energy calculation. Okay, hope that questions are easy. And that's it from this particular video, and we'll meet with another one soon. Thank you.